In this part of our discussion on the inputs to GLHEPRO, the load specifically, we're going to look at an example building, and we'll just run through the process. We have a live demo that'll be part 4, so this is kind of an overview of what it would look like, and then we'll go on and do the demo live in part 4. So this is an existing state park lodge. In other words, it's a small hotel. And they're considering replacing the existing system with a ground source heat pump system. This is actually the subject of a capstone design in mechanical engineering in the spring of 2020. So I've got some students who are working on this now. Their approach was to make I'll call it a rough energy model in Energy Plus. So by that I mean that I think it's pretty much a brick-shaped building, which is not quite right, but the surface areas in each direction are about right. The window area in each direction is about right. And they use that then to estimate the monthly electricity consumption, and specifically what they used then were actual utility bills with had kilowatt hours, and they basically adjusted the model so that it would predict about the right monthly billing. So yes, the hourly loads are determined from this revised model. They may not be perfect. You may even see some things you think, well, maybe you should have done this differently. On the other hand, they do match the monthly loads, which are more than you can say for some energy models done at design time. So anyway, so I think this is certainly a reasonable approach. The peak heating load, these are the heating loads in kilowatts for each hour, or you could say they're the energy kilowatt hours for every hour, but either way, they're the kilowatts that occur each hour. The peak load is right about there, February 3rd. It occurs late in the evening, but not all the way, not at 4 or 5 in the morning, which might be what I would guess if I was just going to think about a typical building. But you can see this is the load for the day. So the night, in the early morning hours of that day, maybe gets up to close to the peak. It's not that much different. Then during the day, the heating load falls off as there's maybe more occupancy and sun shining through the windows and so on. But then at night, it starts to climb back up again, and it peaks around 11 p.m. And then I looked at the next day, and it doesn't fall off all that much, but just falls off a little bit. So it's reasonably flat. But the peak occurs that particular late in the evening. Okay, so what the tool is going to do is it's going to make a model, or it has a model built in, and it computes the temperature response both for the actual hourly load for that peak day and for a peak day that has zero load part of the time and then has the peak load. I say zero load part of the time. It's a little more complicated than that. This load here, right, could be translated from heating load on the heat pump to heat extraction, right? So if we're, say right there, we're providing 100 kilowatts for heating, the COP of the unit's 4, right, will only be extracting 75 kilowatts from the ground, right? So there is a plot here that you could make that would be the heat extraction from the ground, right? And maybe, like I said, maybe at that hour it's around 75. There's also a monthly heating load, and so if, say, that's 40 kilowatts of heat extraction, then we would actually superimpose a load that would be the difference between the heat extraction load with the actual and the constant for the month, and that would be the load we'd superimpose on the ground heat exchanger. So in the Introduction to Ground Heat Exchanger Modeling lecture, there's some explanation of the superposition process. We won't get into the details here. But that, when we superimpose the actual heat extraction rate that would occur over the monthly average, and we find the temperature response over the day, right? What's actually going to happen is towards the end of the evening, there will be maximum temperature decrease. But if we divide the hourly temperature difference from the average, monthly average at the end temperature, if we divide that by the maximum for the day, right, then everything's normalized to 1 for the actual temperature rise or fall. It's all normalized to go to 1. And then the peaks, the rectangular peak loads that are equivalent, we do those in the same way. So we have here an 11-hour peak, a 14-hour peak, a 17-hour peak. And the 11-hour, you see it wouldn't quite hit. The 14 is, I think that's just about the closest. And if we use 17, we'd overpredict. It's fairly flat in here. So the difference between, say, 14 hours and 13 hours is probably less than half a foot, or yes, quite small. So we'll use the tool to actually investigate different ones, and we'll even look at the difference between 13 hours and 14 hours and so on to figure out what the best is. Okay, for cooling, right, if I didn't say this already, the students have a cutover day that they picked out based on the load profile where the whole building switches from cooling to heating. Right, and that's why in the heating, right, there's 0 from that date forward. And from cooling, there's, it's 0 in the winter and early spring, and then 1 day in March it switches over. Right. And of course, in reality, probably during the shoulder season, there'll be some simultaneous heating and cooling. But the design's mainly going to be driven by the peak load. In fact, it's mainly be driven by the peak cooling load, which occurs on August 31st. And you see there's some loads very close to that earlier in the month, but of course, the longer we reject heat over the summer, the higher the temperatures are. So the sort of the latest, highest peak is probably going to drive the sizing. Okay, again, the peak cooling day. This plot is based on the convention that used by Energy Plus, which is that cooling loads are represented as negative loads. You can put the loads in the tool either positive or negative. I mean, you have to keep the same convention the whole time, but it can figure out which one you're using, but it will always plot it as if they're negative. So the quote maximum cooling load, the highest negative load, occurs here in the sort of late afternoon. Right, and if we try in the tool, we will try some different durations. So you see a 3-hour max is not very close. A 6-hour is getting closer, but it's still a little under. A 9-hour just goes a little bit over 1, so it's probably about right. Now, when we do the live demo, we'll go back and we'll look at 8 hours and 9 hours, and I wrote them down and figured out which one's closest. You pick that one. What you'll also see is that if you then go back and check the sensitivity of GLHEPRO to the design, you'll see that there's the difference between 8 hours, 9 hours, 10 hours. This is all within about less than a foot in the peak in the depth. So it's really very when we're very close in the predicting close to 1 in this plot, a little variation on either side doesn't make that much difference. Right? We get the biggest change when you go from 0 to 1 and from 1 to 2, and so on. But as we get close for a load like this, it's a small difference. Okay, so that's kind of an overview of the sizing procedure, and then in part 4, we'll do a live demo of this, which, believe it or not, will take longer than just telling you what the results are. So that's it for part 3.